think about. Okay, so why is chlorine having a specific charge, right? So, and yeah, perhaps this will help you, right? So that's like pretty detailed scheme. To be honest, we have the so-called arrow pushing here that shows the movement of the electron pair, right? So we have the dissociation here going on, so things get ionized. So, but now we need to figure out like one more thing, which will be the charge essentially, right? So charge on the Cl or chlorine. Okay, great. So we have some effort going on here. So thank you for that. Bless you. And now what do we have in terms of responses? Okay, so people say usually -1. Okay, great. So there's going to be a -1 charge. It's negative. So, and then it has like an extra lone pair. So that's a good way to think about it. So essentially, yeah. So basically, if you look at this chlorine, it has essentially around itself in the outer energy level, like 6, 7. But now you have 8 electrons, right? So just count dots. 7 dots for chlorine, right? Like so, and now you have 8. So basically you have an extra electron, or yeah, so it makes it like extra lone pair essentially, right? So if you think about it. So yeah, good job. So yeah, track your electrons as well, and then yeah, you'll be like in a better shape. So this can actually be applied to carboxylic acids, with the exception that you will have, instead of chlorine, you will have the oxygen, right? So which we'll see later how it transpires. So because carboxylic acids, if we recall the like functional group structure, just in general, so they should have or they must have the oxygen, right? Even 2 oxygen atoms. All right, so now let's move on to like what we have here in part 2. So I think we're talking quite a bit about the formation of hemiacetals and acetals, right? So then we have we have the activity for this purpose as well. So, and yeah, so then we're talking about the ketones and how they add alcohols to themselves. So then we had some examples as well, right? So, but now let's see if we can figure out, right, actually what different molecules are, right? So if you look at this slide, so here we go. So like what happened? So this particular question asks us to identify those molecules as hemiacetal, hemiketal, acetal, or ketal, right? Show and then we need to show the reagents and the starting materials that led to them. So that's probably a good question. Then we will see how it kind of like connects to activity number 1. So, and then for some of you, so I posted this like well in advance yesterday. So that's a chapter 14 worksheet number 4. So that's kind of available already. And then here, the question is a little bit more kind of a general, right? So we need to start with an aldehyde and some alcohol, right? So the only restrictions are 5 carbons and 3 carbons respectively. And then we need to form a hemiacetal, which will then react with the same alcohol to form acetal, right? So it's pretty straightforward. So it's about acetal formation. So in this kind of like 2-step fashion. So that's like one premise for today. So maybe somebody already can kind of like show that, right? So, but for now, let's take a look at some kind of like examples that go backwards, right? So here we are presented with the molecule, right? So that's going to be our product, right? So which we want to make basically from the starting materials. So now here we want to identify those starting materials, like what they are, right? So that's basically going to be the question. So let's take a look at maybe A, for instance, here, right? So like what do we have in this case? So looks like we have something that doesn't quite look like an alcohol, right? So, but at the same time, we have this combination of atoms, which will look like the combination of atoms in hemiacetal, right? So here we go. So like, what do we need to have in the hemiacetal? It's going to be HOCOC, right? HOCOC combination of atoms. right? And then here, if we take a look at molecule A, we'll have H. So what do we have? We'll have HOCOC. So perhaps that's going to be the case. So let's try to highlight it here. We have COC, and then we have H and O as well, right? So that is the molecule here. Okay, so let's see how we can potentially make it, right? So if we look at this combination, right? So like inevitably we need to have the carbon-oxygen bond in hemiacetals. So that's the one. This COC piece is in front of us in red. So we can assume that, for example, this like ethyl oxygen piece came from the alcohol, right? So, and then also, like, as you remember, at some point we are going to form the OH bond, right? So, like, we can see this OH bond quite clearly in this molecule. So, if we recall the general example, so looks like when the aldehyde and an alcohol reacts, right, we just need to go through like several cases, right, basically. So the hydrogen was coming from the alcohol. So maybe it was coming from actually ethanol here. So we have the ethanol piece here quite clearly, right? So it's like that ethyl oxygen without hydrogen. So that potentially came from the alcohol. So the hydrogen in the blue circle came from the alcohol as well, right? So the rest of the molecules should be, could be an aldehyde, right? Let's see if it is feasible. So I'm just going to transfer the drawings to the white paper and see how that goes, right? So here we just say, okay, well, looks like this. Let's see. So where is this color? So the H comes from an alcohol, right? According to the general scheme. So once we form this kind of like new OH bond in our hemiacetal, so like we can recall from the general example slide that H came from an alcohol, right? So then perhaps this piece here, so this one, O ethyl, right, also came from an alcohol. So then if we kind of like mentally connect them, so we'll get nothing more than an ethanol molecule. So then if you look at the leftover combination of atoms, right, you'll have the cycle, right, which kind of like doesn't participate directly in the chemical reaction. It is just carried over as like baggage or something, right? So, and then you have the central carbon, so which comes from an aldehyde or a ketone, right? And participates in the chemical reaction. So, but if we assess the situation here, we'll have the cycle, and we have carbon, oxygen, and H, right? Everything else belongs to the alcohol. So COH, so this combination of atoms looks like an aldehyde, right? So let's try to draw that maybe on this kind of like on the piece of paper here and see what happens, right? So it's going to be our part A. So, and I think activities are kind of a little bit easier. So because you just need to go straight in the forward direction from the reactants to the products, right? So let's see what happens here. And then we'll just like check if we get our target structure, which is structure A, right? So here we kind of need to think in reverse. We go from products to the reactants. So we need to like figure out what the reactants were. Okay, so here we go. So we'll have our aldehyde, presumably looking like that, right? So that's going to be the piece which is kind of like not circled, right? So you can see this like hexagon COH. So hexagon COH, we just need to make it in a like sensible fashion. So because we need to have the double bond, right? So carbonyl at the end of the day, so is possessed by an aldehyde. So the next step will be to take a look at the alcohol part, which is presumably this like chain, right? So we have what do we have here? We have O-ethyl, right? So we'll have O-ethyl, CH3, CH2, then we'll have oxygen with an H. Okay, so now let's see if this combination kind of makes sense in terms of giving us the product, right? So maybe some of you will think about some like more complicated things, right? So because not always we are going to have like A plus B equals C, right? So this like proverbial C product can be made maybe from like A and X, right? Or maybe X and Y. So that's something to keep in mind. So not always kind of the reactant will be like exactly like only like one pair of combination, one pair of chemicals, right? So it could be some kind of like different pairs as well. So, and maybe somebody of you will see something that I don't see, right? So that's like also entirely possible. So now we'll have our conditions, right? So we'll just follow the good suit here. So it's supposed to be done in the like acidic environment. So now we'll show our dotted bonds, right? Which will show the formation of the new bonds, right? So according to the example slide, we're going to form this like OH bond between the oxygen from the carbonyl of the aldehyde and hydrogen from the alcohol. Great. So that's one. And then number two, maybe let's make it blue for the difference sake. So it's going to be like this. So it's going to be carbon-oxygen bond between the carbonyl from the aldehyde, right, and the oxygen from the alcohol. So now let's see what happens. So we are going to redraw some things which don't react, such as this ring, for example, right? So then we'll have the carbon. So just be careful. As you previously mentioned, we are going to change the hybridization, right? So, and we are going to have here oxygen, that's a top oxygen, right? So I just like put it literally here in the same like geographical location. So this will connect to the H, right? So consequently, you cannot retain this double bond between carbon and oxygen, right? So you need to make sure that the oxygen is like divalent, right? And then that's what you like check this box here, right? So maybe lone pairs, all good, right? So now we want to deal with carbon, right? So carbon lost this pi bond, presumably was broken, right? So now it's like no more. So now you have only sigma bond left over. Okay, all good. So then we move on, right? So we're going to make this carbon-oxygen bond, right? And then it's going to be looking like this. So that's the oxygen from alcohol here, right? So then we'll attach the ethyl group that kind of like doesn't participate directly in the chemical reaction, but it kind of like still needs to be in there, right? So that's the one. And then does it look like the molecule A? So looks like it does, right? So we kind of like check all the boxes as we check the situation. Okay, so that is going to be our hemiacetal, right? So hemiacetal is the product. So don't worry about its name, just kind of like know the general term for that, right? So when you have the combination like that, so then you'll have the hemiacetal. So, and then most importantly, okay, combination like that, it's like could be like vague, right? Unless you say, well, there's going to be a carbon, right? So this like with an arrow with a particular hybridization, right? So SP, like what it is here, right? So you need to answer that. So then we used to have the other hybridization here, right? So, and then we need to have like OH, O alkyl chain, H, and then some sort of chain which was related to the like aldehyde molecule. So, and then also here you have one exactly molecule of aldehyde, and then you have one molecule of the alcohol reaction, right? So mind your stoichiometry here. That's going to be kind of important because it will tell you what product you are going to obtain. Okay, great. So that is our hemiacetal. Looks like that's what we have formed. So now let's take a look at maybe question B, right? So this one will be a little bit different. So if we look at what's it going to be called? Let's take a look at B here, right? So we'll have something like that. So we have the central carbon with the two oxygen and ethyl groups, right? So, and we have another combination of atoms. So yeah, it's going to be just kind of like maybe helpful to look at the pieces, right? So which we can identify. So I'm going to be looking at this, right? So C, C, and C. So looks like this comes from a ketone, right? So, and then those two things in blue came from an alcohol, right? So why do I think it is a ketone, right? Because ketone is supposed to have carbon, carbonyl, and carbon, right? So that's kind of like what we almost have in our red region of the molecule, right? So then if you look at this kind of like O alkyl part, which is in this case specifically O ethyl, looks like this came from an alcohol, right? So because for the alcohol to be made from the blue part, we just need to add hydrogen, right? So at the right place to the blue parts, and then we'll get the ethanol. So it's going to be like nothing more than that. So here we go. So let's take a look at this case. So maybe it's going to be part B. So it's going to be a little bit complicated, but it's okay. So looks like our kind of like gamble here is that it's going to be the ketone, right? So we are betting on the ketone. So let's draw that ketone. So we need to have the aromatic ring, which will be looking like this. So that's number one. So then we'll have the like central carbon, which is supposed to be carbonyl, and we'll have the methyl, right? So to make the ketone out of that, so all you need to do is just attach the oxygen, and now you have the ketone. You have carbon, carbonyl, and carbon again. So that is all good. So now we need to kind of deal with those blue parts, right? Which are presumably coming from the alcohol. So let's do that. So here we go. So we'll have HO and ethyl, CH2, CH3. So typically, you have two stages, right? So when you make this, by the way, will be, so if you look at this combination of atoms, right? So you need to have like CO, CCOC, right? Something like that. So I don't quite remember them, but as you kind of like look at how it was made, right? So you just need to inevitably look at the parts, right? So then unravel that into those smaller building blocks. So now let's see if we can kind of like make compound B, right, from our presumption, right? So it looks like we used to have the ketone with an alcohol. So again, conditions, reacts, right? So what's going to happen is that we are going to form the, again, same bonds as previously. OH bond will be formed, and then CO bond will be formed too. So here we go. This is our first product, which will be a hemiketal, right? So because we kind of react ketone and one molecule specifically of alcohol, it's going to be like semi or hemiketal, right? So because we can still add the second molecule of alcohol and make a ketal. So that's just how the convention went. So we'll have here the following, right? So we'll have CH3 and the phenyl group will kind of like survive, right, in their original forms. Then we're going to have the OH bond, okay, very good. And now we're going to have our first carbon, oxygen, and ethyl piece in the molecule, right? So that's done, right? So that's the one that we get. So now, if we recall, we can add to this another molecule. So here I'll show something different, right? So that's going to be done in acidic conditions. So you can put them under the arrow sometimes. And what's more important, right, for the reaction will be put on top of the arrow. It is just to save the space, right? And then kind of like write in a more rapid fashion. So now here you have your hemiketal, that's the one, reacting with another molecule of alcohol. So there we need to recall that, okay, like water will be eliminated. So we can circle out the water like this and that, right? So it doesn't matter who loses what, right? So, but eventually it's going to be OH and H, or maybe H and OH, right? But either way, you're going to lose the water molecule in this situation. So here we kind of like decide to do it like that. So perhaps your hemiketal will lose OH, and then alcohol will lose H. So, and then this will lead to the formation. So we'll have those kind of like blue electrons now available on the carbon and oxygen. And now you will see like nothing more than the covalent bond, right? That's going to be your best guess. So we'll have the covalent bond formed just like so. And now let's see what happens, right? So if we get the right compound here. So we're going to continue, right, in acidic conditions and everything. And now we'll just redraw something, just kind of like don't forget those things. So you have carbons, so then the methyl will be redrawn with the phenyl group. So then we'll have our like first O ethyl like this. And then we are going to also add what? carbon-oxygen bond, and oxygen with its ethyl, of course, right? So that's the one here, O, and then ethyl again. So CH2, CH3. So then we'll have the blue electrons, kind of like signifying the covalent bond. And now it looks like we have made part B. So that's like very nice, right? So that's gonna be kind of like some things to think about. So maybe I will put more of them into the practice session. So, but for now, let's get to something kind of like more maybe easy, right? So that's going to be activity number 1, right? So here we need to have a little bit of a review, if you will. And we are going to start. Okay, so it's going to be like a 2-part question, actually activity 1. So we are going to start with an aldehyde and 1 molecule of an alcohol to form a hemiacetal. Okay, so go ahead. So like we have some way to the new people, so to speak, right, to present, and let's give it a try. So here we go, and yeah, activity number 1. Take it away. Okay, so we have an aldehyde and alcohol, right? So look, we start with just the reactants. They are already kind of given to us, and we want to show what happens, right, upon the formation here. Okay.
I think I messed up already. Just ignore this part and stuff.
Yeah, so you can just cross it out somehow, right? So yeah, this will be an aldehyde. So, or if you have a bond, you can always kind of, in this case, put the H at the end of the bond, and then this will make the bond to the H specifically. Okay, great. Then we have 1 alcohol. So like, what happens next? Let's try to show it, right? Okay, so we have the conditions, very good. So that's doable, and you can use the dotted lines maybe to show what bonds will be formed, right? So that could be helpful. So granted, you have lots of different colors here. So like what new bonds are we going to form, right? So let's see if I can recall it. Okay, so it's going to be carbon to oxygen, right? Or like, yeah, oxygen to H. Yeah, that's good. So, and then what's the other one? So now we have the other bond as well. So that one is between the carbon and oxygen on the alcohol. Okay, good. So yeah, that's going good so far. So let's see what happens next. All right, so yeah, well done, great. And then we even use the skeletal structure, right? So like, which is kind of nice. All right, so now, so like for the second individual, so what can we offer? So it's gonna be the same alcohol to form an acetal. So who wants to form an acetal? So we have new people. So go ahead, let's do that. And then, yeah, there'll be like many more opportunities as well. So if like the veterans eventually would like to go, then they will be able to have a chance. All right. So now that's the second part, right? So that's nothing more than just the kind of like step-by-step synthesis. Even though it's 2 steps, it already counts, right? So we need to redraw basically this like big molecule that we formed in the previous step by Ariana. And now let's see what happens next, right? So don't forget the building blocks, right? So that's just going to be your exercise of redrawing things. Quite important sometimes. So because people do forget a lot of stuff to redraw. So that's why we draw attention to this. Okay, and we need to use the same alcohol, right? The alcohol was just ethanol. So this hemiacetal will react with ethanol.
Right, because she.
So not quite, right? So first of all, like let's make some adjustments. So underneath show plus this molecule, right? So yeah.
But then on this second one, she drew there's 4 carbons.
So let's see. So you have, so this is your starting material in red, right? So now like underneath show like plus this molecule, right? Plus ethanol. So that's where I need to be. So CH2, yeah. Okay, great. So now let's show the elimination of water, right? So just H from alcohol, yeah, that's right. And then OH from the alcohol will be eliminated. So alcohol, no, don't touch that. This one. Yeah, that's right. So, and now we'll need to connect the oxygen and carbon, right? So to make the final molecule. So we already have, okay, so we just need to literally make one switch, right? So in this case, so you have O something, right? So that doesn't look, okay, so yeah. So basically you need to have another oxygen with the ethyl group, right? So that, yeah, that's like what you will have here. So great. So yeah, that's going to be our final molecule. So yeah, there was quite a bit of scramble going on, but eventually it was done, right? So yeah, basically you are going to like form all the right bonds. So and then here the like most important parts. So we're going to form this carbon oxygen bond, right? So that's what you will have, and now you're going to make basically your hemi not the hemi, but the full acetal, right? So here, look at this kind of like central carbon in this case, right? So like with the black arrow, that's going to be the carbon, right? So it has the attachment to like O alkyl in this case, right? So then you have another O alkyl. So, and then you have carbon, this central carbon has the connection to the H, right? CH bond, that's going to be your sign of acetal, right? So this kind of like will become easier as we go through more and more examples. That's why there are like activities, right? That kind of like prompt you to think about those questions. All right, so yeah, that's the one. So the only thing, so again, speaking of like drawing stuff, right? So if you are using the skeletal structures, right? So just like something to be clear. So what I want to highlight. So this is a carbon, right, in red. That's another carbon. And now you have this bond, right, to the oxygen. So then there is no carbon here. So carbon here, oxygen. There is no carbon in between, right? Consequently, you are going to have just ethanol, right? So just think about that. So that being said, we have carbon, carbon, and we have some extra stuff which is not needed, right? So that's extra as well as here. So we have ethanol, right? So 1, 2, and then this carbon is not needed. So just count your carbons, right? So perhaps I'm gonna kind of like again show some reinforcement, so to speak, right? So if you wanna make proper drawings, it will be like that, right? So let's draw maybe like ethanol, right? So ethanol is CH3, CH2OH. So all I need to do for ethanol is that, right? So, and then I can show maybe with the blue color the carbons where they are. So that's carbon here with the respective H's, right? So it's your duty to count H's here and count H's there as well, right? So now that's it. So here you have at the end of this line, you don't have just that, right? So if it's going to be, let's imagine just that, you are going to have propane, right? So carbon, carbon, and carbon, right? So that's what we kind of are supposedly have at the end of the line. But here now you have explicitly oxygen with H, right? So that means that at this point here, you don't have carbon, right? So carbon is only here, bond to oxygen. That's it, right? So that's your ethanol. If you want to show propanol, right? So because Olivia started kind of like doing like 3 carbons and 4 even somehow, right? So that's okay. So, but what I need to kind of like draw your attention to is going to be like that. So you have a couple carbons. If you want to show propanol, it will be like that. Okay. So that's a carbon. So for propanol, first of all, we need to have 3 carbons total, right, in this alcohol. So just do that. So that's the 3 carbons. And now if you want to show the oxygen, you will need to have the bond that will stem from this carbon to oxygen with an H. Now you have the propanol. So now you can kind of like see the difference, right? So like 1, 2, 1, 2, 3, 3 lines, right? So a little bit more lines. So just count your bands. So every band is a carbon, every end is a carbon, unless there is something on the end, right? So for example, so you can do like that, right? So maybe let's take a look at the ketone, right? So ketone will be like this. So that's your ketone molecule, right? So that's the one. So like 1, 2, 3, 4. So here we assume there is a carbon, right, on this end. But if you say, oh, I kind of like messed up. I wanted to draw an aldehyde, but I drew the ketone. Well, no big deal. So that's how you can convert this ketone into an aldehyde very easily. Just show an H explicitly. And then like here we can say, okay, well, if H is shown explicitly, there couldn't be another carbon, right? So what's that kind of like pentavalent carbon? Doesn't make sense. So this now becomes your aldehyde quite easily, right? So if you think about it. So again, kind of like what's not shown explicitly, it's carbons, right? So like other atoms, if need be, we can show them explicitly. So yeah, that's just like a little bit of the segue here. So, but now let's take a look at activity number 2. So let's see if we can make a hemiketal and the ketal then. All right, so like we have some candidates happening. Okay, so let's go ahead and then give way to the new people and see where we are, right? So hemiketal and then a ketal. So it could be like 2 people activity. Could be 1 person activity, who knows, right? So only the practice will show. All right. So take it out or away, some of that. All right. So let's see what's going on with those hemiketals. So if we count the carbons, looks like indeed we have 5 carbons in the ketone and we have 3 carbons in the alcohol. Great, great. So yeah, that is well done so far. So we have the conditions. Good. It's reversible process. Very nice as well. And yeah, so this is put it down a little bit so people can see. Okay, good. So this is going to be the hemiketals. So now, do you want to make the next step?
You want me to?
Oh yeah. So
Oh.
if you want, so you can go ahead. So yeah, you will do like 2 steps in a row. So that's going to be quite historical. So now we have the hemiketal, which is going to be used as our reaction. So it's like, for example, there grows a chicken, right? So chicken is a product from the farm, and then you take the chicken and make a curry out of that. Then like chicken was the reactant, right? In a sense. So same exact thing happens here. Okay, great. So, yeah, well done. Awesome. So, yeah, that's your very rapid dealing with activity number 2. So, yeah, once you draw that, so it's all good here, right? So just like make sure that, like that's what my advisor was talking about, right? So that there is like the space is managed properly, right? Because otherwise it looks like this carbon, oxygen are floating in space somewhere. Just kind of try to draw them like more together, right? I would draw them maybe like that. So oxygen, right? So with the ethyl, so it's going to be, well, you have the propyl, right? So that's the one, right? So then you have your carbon bond. So here could be like straight. Okay, that's fine. Oxygen with another propyl. So now it's kind of like more snug, so to speak, right? And then this also seems a little bit disconnected to me. So like put it more like to the center, right? So you're kind of like right in the middle of the C letter. So, and then you have your like whatever, like alkyl chain. This one kind of is a little bit offset as well. So just put it in the center, right? So and then you're all set. So because it stems from GenChem, right? So when you would draw the like loose structure for the carbon atom, it would be like that carbon, and you have like dots kind of like centered equally around it, or whatever the proper way to describe it, right? So they're kind of like there, like on the sides and then top, bottom. So it's all like symmetric, right? And then you would add your stuff here, whatever it might be, to those electrons. Maybe it's going to be like some kind of group, right? So maybe you will have some sort of like OH bond. Maybe it's going to be, I don't know, whatever it could be, like phenyl ring. So it becomes kind of like very like aesthetically pleasing, right? So, and then that's it, right? So that's something to keep in mind. So, but yeah, as you like recall those like 4 dots, which also makes sense because you need to have like tetrahedral formation, then you'll be like in a good shape. All right. So then what else? So now let's see. So these ones, I think I'll try to like put C and D, yeah, into the practice session on Friday, which is tomorrow, actually. So, but now let's move on to the next topics, right? So, what do you want to do here will be, okay, so like we're going to take a look at, so this one is kind of like complicated case. So let's take a look at better at, I would say, synthesis, right? So like this one will be more important to us because it's like part of the review actually. So activity number 3. So like we have a little bit of the trick question here. We have the alkyne. We need to make an alkene from it, and then alcohol, then a ketone, right? So that's going to be part A. So that could be probably done by like a couple people. So because we have several transformations here, and then this task will leverage your fundamental like knowledge relative to this course already, and the stoichiometry as well. So reaction conditions, all that stuff. So it's going to be a little bit more holistic. So let's spend time on that, and then we'll get to the acids, I guess. So let's see. So start with an alkyne and make an alkene from that. Okay, so go ahead. Let's give it a start. So maybe we'll do entire activity 3A. So right now we're looking only at activity 3A. And yeah, a little bit of the review because of the nature of it. All right, so let's see. So we have a bunch of colors here, so feel free to use them. What we got?
They want an aldehyde or they want a ketone?
So I think it said the ketone.
Ketone?
Right? Yeah, that's right. So you'll make a ketone, and yeah, eventually. So that's some sort of alkyne. Good. So now show us the hydrogens as well on the carbons, right? So, and then we'll need to like see that we don't have any hydrogens somewhere, right? So great. Yeah, good point. So like we have an alkyne in the middle, right? So it's not a terminal alkyne, and then alkyne somewhere in the middle of the molecule cannot have any hydrogens because it maxed out on the bonds already. So then we have hydrogen addition here going on, and then we make an alkene. Okay, good. So now the only thing, so do you remember the conditions for the hydrogenation? It's H2, right? So you add H2, and what's the catalyst? It's a metal.
H2SO4.
It's
Oh,
Pp,
platinum.
platinum. Good. So don't confuse your H plus and H2, right? So yeah, just cross out a plus. That's why I'm asking them, what's H plus? What's hydrogen, right? So they are similar but different. So, and then, yeah, that's kind of what is shown here. So now we continue. So to the next step, we add H2O in H2SO4. Okay, that's like clear cut. No problem here. And then we're going to make some sort of like secondary alcohol. This molecule, yeah, so we can potentially make 2 isomers, right? So because where you put the OH group will make you like a different alcohol from like case to case.
What does it want
But that's one isomer, right? So now we can just continue to the next stage. I think it is, so we made the alcohol, and now you're one step away from the like final step. which is going to be the like whatever you form. So now we have the secondary alcohol, by the way, oxidized, right? So all the like steps are like recallable, I would say. So we did see them in the past, and that's what we make. Okay, yeah, good job. So yeah, that's the one, and this is your multi-step synthesis. Well done. Excellent. So here we go. So like one thing to keep in mind, it is just more of the, I don't know, like noticing kind of like skill, right? Paying attention to the details. So when you have some kind of like alkene, right, which is not necessarily symmetric. So you have this alkene, right, by Lucas, and it has, you see, 1, 2, 3, 4, 1, 2, 3. So this is non-symmetric. You have a different chain lengths of alkyl substituents attached to the sp2 carbons. Let me just say it that way, right? So, and then you need to know which carbons are sp2, these or those, right? So these are sp2 carbons right here. So like on the alkene. So, and then theoretically, what could happen is that you will form different isomers. Let me show you maybe some kind of like more glaring case, right? Such as this one, right? So maybe you have an alkene, which is going to be looking like that, right? So let's give it some aromatic stuff, right? So then you have CH, that's your sp2 hybridized carbons, another CH, and CH3, right? So now the question for you all, right? So let's imagine that you are going to use your H2O, right? Or like HOH as the hydration agent. And now you have the conditions, right? H2SO4, right? So that's, let's say it is case A, right? So now case B will be looking like that, right? So let's imagine we're also going to have the alkene, but I'll call it like symmetrical alkene, right? So then you will see what I mean by that. So it's going to be looking like that. So let's maybe make isopropyl and isopropyl. And then the reaction conditions will be the same here. We hydrate this alkene in the presence of H2SO4. And now that's your like a little bit of the critical thinking here, right? Or something along those lines. So now, okay, so the question to make a question to what's it called? Google Classroom. So let's ask that. So here we go. So how many isomers can we make in A and B? B. So that's all right. Let's go. So let's do that. So yeah, think about that. Maybe like talk to your peers, talk to yourself, right? And then that's what we are going to take a look at here. So yeah, when you draw some sort of like answer those questions, right? So sometimes you can run into situations when you have like various isomers potentially, right? So right now, so like we are doing, I would say like lots of people do a good job just kind of like making the reactions possible, right? So, but now there could be some kind of like further advanced details, which will like ask you to think about, oh yeah, can we like form like only one product no matter how the attachment goes, or can we form isomers, right? So that kind of like gives us brings us back to our original like whatever presentation number 2 when we're talking about the isomers, right? So and how they are different in terms of the arrangement of the building blocks in your molecule. So that's something to think about, and that's what you can see in these situations as well. So how many isomers will you form in A versus B, right? So, and like whoever answers that, so they might as well present that so they can show the isomers for A and B. So it's going to be like a nice extra activity, maybe like for a new person who like reviews, right? So that is an option as well. You can show the isomers. here for us. All right, so let's take a look at what we got. So we have some efforts going on. So yeah, it is just about putting together the like H and OH pieces, and then you will make your products, right? So according to the hydration of alkenes, so they need to like hydrate it in like specific way. So let's see what happens here. And then you'll just need to like pay attention to the arrangement of the building blocks, right? So that's what this will be about to a large extent. Okay, so we have some good calls, right? So like what do we have here? Like we have several responses. Okay, thank you for that. So we have exactly like one at least right answer, right? So that is awesome. And if you want to give it a try, you might as well kind of like do that. So that will bring you extra credit points as well for the third exam. So it is just the hydration of the alkenes. So nothing crazy here. Okay, let's do that and then see what we obtain right after the hydration of these two products. Quite exciting. We have different colors. So that's awesome too. And we have 2 in 1. So that was the exact answer. Right, so 2 isomers in case A and only 1 isomer will be formed in case B, no matter how you can like put like H and OH. Because remember, so the H and OH pieces can go to either former sp2 carbon in the alkene. Okay, great. So that is being drawn. Okay, so that is great. So that is isomer 1, right? So, and you see just look at the attachment of the OH piece, right? So it's kind of like a little bit far from the, let's say, aromatic ring, right? Kind of like 1, 2 on the second carbon from the aromatic ring. So, but now this OH is on the first carbon away from the aromatic ring. So then if you want, you can do like B as well. B will be even easier, right? So yeah, so whilst you are there. So let's see what the isomer will be for B. So you have isopropyls and symmetric, right? Symmetry makes things easier a little bit, and you have just like less options.
Is this just a double bond in the middle?
It's double
Oh,
bond,
okay.
yeah, that's right. Yeah, it's double bonds, so I think, yeah, it's like tetravalent and carbon, all good, yeah. It's not Z, it is double bond. All right, and yeah, so that's one way, right? So then if you want to switch OH and H in terms of where they go to the, it's going to be the same compound, right? So like literally like only one isomer. So yeah, because if you flip your right molecule 180 degrees, you will like, be able to superimpose it on the left molecule. Okay, so yeah, that's the case, right? So here we just pay attention to the building blocks. So let's say aromatic carbon here, 1, 2, 3, and then on the third carbon we have the OH, right? Let's imagine we are going to count these carbons, carbon, carbon, and carbon, right? And then you have OH on the third carbon from the aromatic ring. So here, 1, 2, and OH is on the second carbon. So that's already like a different isomer. It's like, yeah, the same kind of like molecular formula, right? So, but the different arrangement of the building blocks. So, or you can say maybe this OH will be closer to methyl, and in this case, OH will be farther from methyl, right? So that's another way to look at this same situation. So here, no matter what we do, we are going to obtain the same molecules. So those molecules are superimposed, right? So you just need to flip it 180 degrees, and then they will kind of like be superimposed completely. So yeah, that's kind of like going to be the catch here. And then yeah, well done. So now let's move on, I guess, to what else do we have? So here we go. Okay, so that's going to be switch of the slides. I'm going to go to, I guess, at this point, part 3. Okay, so we have lots of multi-step synthesis today. So a little bit of the review what like alcohols or like aldehydes can do rather, right? So this is going to be again like a pathway towards the new chapter. So here you go, right? So turns out, like if we recall again, a little bit of a review. If we started with the aldehyde, previously people were kind of able to make alcohols from that in a lot of cases, right? I think it was the case on exam 2 potentially, or exam 3, whatever we had just recently, right? So, but if you apply the strong oxidizing agent to aldehyde, you will make the carboxylic acid, right? So remember, so like the sort of you will bypass the alcohol, which can be formed, and then it will be like that. Let's put it into the parentheses. So R so no, sorry. So you are starting, right? So like I messed up a little bit. So here your starting material will be an alcohol RCH2OH. So but then you are going to make an aldehyde by oxidizing, right, the alcohol. You oxidize the alcohol. Typically, with a mild oxidizing agent, we can just attach, remove only H's, right? So we basically like remove one H from here and this guy, right? And now you have your CHO piece, which is going to be the aldehyde, right? So that's how the like oxidation works for alcohols. So you can make aldehyde. So a little bit of the review. So, but then if you continue oxidizing further, right? So now you oxidize aldehyde, and then with the, typically it's done with a strong oxidizing agent, because here you not only remove H's, you actually don't remove H's, you add oxygens, right? So that requires a little bit more of the oxidizing agent, right? So that's why we need to have a strong oxidizing agent here. So, and then if you look at this situation, you are going to increase your oxygen count from 1 to 2. So hopefully it will come back. Let's see. So let's see what's going on. Okay, so this is our slide. Okay, great. So everything disappeared, what I have been writing, but it's okay. So here we go, right? So your aldehyde only featured one oxygen, carboxylic acid will feature two oxygens. So that's like a definition of oxidation in organic chemistry, right? So you increase the number of oxygens. We are all good. And then this will be kind of like flow into chapter 15 at this point already. So what else should we think about? It's a no reaction, right? So if there is a question somewhere on the exam, maybe ketone, you try to oxidize the ketone, there is no reaction, right? So basically that's like done here. So you are not going to like break this carbon-carbon bond. It's kind of difficult to do, right? And then you might run into some complications. But for now, like we are just going to assume there's going to be no reaction when you try oxidize a ketone, right? So that could be like somewhere in the like trick questions, and you'll be like, okay, I know that there's going to be like no reaction, right? Because it's a ketone, right? Not an aldehyde. Aldehyde, yeah, the process goes, right? So, but with the ketones, so that apparently like doesn't work. So, yeah, that's kind of like what we have for now. So now another thing is going to be the kind of going to be the as they call it, a qualitative test, right? So apparently there is a way to confirm that you have an aldehyde in your reaction mixture somehow, right? By the like silver mirror test, right? So basically what happens is that if you have an aldehyde, for example, in your reaction mixture, you suspect that you can add the silver to that in ammonia and in the base conditions, right? So basically here, why do I say that? Because I can see there is a silver ion, right, that you add to the aldehyde. Then ammonia is NH3. And then OH, it is just the sign that we have the basic conditions, right? So that's what we need to have for this particular chemical reaction, like the test chemical reaction, right? Or qualitative test. So we don't want to count how much of the stuff we have, but we just want to qualitatively assess what we have, right? The quality or something like that. So like, do we have an aldehyde quality to this reaction or not? So, and then apparently what's going to happen is that you are going to form some like organic salt, right? So this is going to be a salt actually of the carboxylic acid. That's for the future. So here you can see the carboxylic acid anion actually, right? So it's a little bit modified version of the carboxylic acid with the new counter ion and everything. Then you'll form the ammonia and then water and then this guy, right? So Ag. So that's going to be a pure silver with a charge of 0, right? So which is going to be here on this flask, right? It's going to be kind of deposited inside of the flask, kind of like very interesting situation. That's going to be your Ag with a oxidation state of 0, just like a pure metal, right? So we can also like say it's in the solid form, right? So as opposed to this case, so here, just pay attention, you have the Ag plus, you have the cation of silver, right? So it's not the same as a silver metal, right? So Ag plus versus Ag, just without anything, it's like a big difference, right? In terms of the charge, for example. So yeah, that's just gonna be the thing, right? And then it works specifically with aldehydes, right? So silver 1 gets reduced to silver 0. So because essentially Gen Chem, right, recollection, Ag plus, right? So then you will add reduction in general chemistry was about the gaining or losing of electrons. Well, reduction is about the gain of electrons. So you add the 1 electron and then you have plus and minus added together, it becomes 0, right? So mathematically. So, and then you, because of this math, you'll get Ag 0. So that's going to be our math here. So then you have the oxidation also happening for the aldehyde, by the way. So just like we saw in the previous slide. So you go from the aldehyde to the carboxylic acid in the salt form. So that's no big deal. So, but the most important part is that you can see the change from the aldehyde functional group to the carboxylic acid functional group, which is going to be in green here, right? So let's put it in green. So that's your carboxylic acid functional group, but it's ionized, right? So that's an important but that I add. So then there's a test, right? So like potentially what could happen. So these are kind of like things that can be identified with a silver mirror test, right? So you have your, let's say, aldehydes, A and C, and then you have cyclohexanone, right? So if you have a cyclohexanone, you need to realize that this one is a ketone, right? So it is a ketone molecule, which will not be necessarily reacting in this test, right? So because we want to say, well, the test, right, this qualitative tolerance test is for aldehydes only, right? So, and then if we see the ketone here, then this will be kind of already like a like critical question, right? So cyclohexanone by nomenclature is not is not an aldehyde because it doesn't end with al, right? So pentanal or this guy, right? So for which we just see the structure here, we can identify the this COH aldehyde functional group. So and then so like maybe we can show the what's that called? Draw both products, right? So we want to show the products that will be formed, right? So here we go. So from the aldehyde, we need to go to the carboxylic acid with a negative charge and the counter ion NH4 plus, which will be kind of like the same, right? So let's do that. So yeah, basically maybe for pentanal, right? So because why not? So some practice. So here we go. So we are going to show our aldehyde pentanal first. So which supposedly contains 5 carbons, 1, 2, 3, 4, 1, 2, 3, 4, and 5, right? So that's the one. So that's your aldehyde, right? So then you are going to oxidize it. So then you'll use those kind of like conditions, right? So oxidation will happen. There is going to be NH3, like argentum. So that's your silver. Ag plus, and then these are our carbons, right, in the pentanal, right? So that's aldehyde. So from that, you are going to form your carboxylic acid, but with a negative charge and the counter ion on it, right? So like redraw the tail like this. So carbon. So here kind of like helps to show the expanded structure, by the way, because you can clearly see what gets added, so to speak, right? And then this is it, right? So that's your ion almost. So put the negative charge on the low, like single bonded oxygen, and now you will put the like NH4 plus counter ion next to that. So that's going to be your salt, right? So this, again, in the brown circle, that's going to be your anion, negative charge of the carboxylic acid. We'll see how they are formed later on. And now let's take a look at maybe case C as well. So this one has the aromatic ring, potentially a little bit more intimidating, but yeah, we'll deal with this. That's okay. So first of all, we're going to start with this molecule, right? So you can call it an aldehyde because you literally see the like aldehyde functional group. And you can also call it like aromatic aldehyde, just like what we use sometimes in activities, or make it like aromatic alcohol. Then you need to like understand that you have the aromatic ring in your alcohol and the COH piece somewhere else, right? And you need to like put them together. So here we have the aromatic aldehyde, which is kind of like just the phenyl ring and aldehyde groups, so they can be put together quite legitimately. So that's your carbon with 4 bonds, all nice, right? So they are connected into like one molecule, aromatic aldehyde, right? So then oxidation will take place in this like Tollens reaction, right? So like with NH3 and Ag plus. I'll just like loosely show those reagents because the point here will be to show the product, right? So that's like what we want to pay attention to now in the interest of time. So then here we go. So we have our, oops, sorry, that's completely wrong. So we have our aromatic ring now, right? So which will get redrawn. And now the action takes place on this carbon, right? So which turns into the carboxylic acid now. And it will have the negative charge here, right? So leave that carbonyl carbon alone, right? It doesn't like get like the charge or anything. It's just like 2 bonds on the carbon. I mean, 2 bonds on the oxygen, 4 bonds on the carbon, and that's it, right? So this guy gets a negative charge. We'll see later on why. And now this negative charge will be counterbalanced with a positive charge on your ammonium ion. So, and that's it. So that is technically carboxylic acid without the hydrogen. Some hydrogen was removed, and then it makes a salt, right, with the counter ion, which is going to be the cation in this case. So yeah, this is something I guess for the future to think about. So have a multi-step synthesis. Look at that. We'll get back to that for sure next week on Tuesday, and we'll finally start with the carboxylic acids as well. So if you did work, please come by to put down your name for the extra credit purposes, and we will be all set. Bye, everyone.